I would like to start our afternoon session and kindly invite all those who will present the papers in afternoon session, as well as I would like to kindly present our afternoon chairman of the plenary session, Professor Alexander Tuzikov. Now he will start, and so I give you a floor. Dear Professor, you have a floor now.
Okay, thank you very much. We are ready to start our session. I would like to introduce our key speaker. Ruslan SALAKHUTDINOV is a professor from Carnegie Mellon University in USA. The title is From Differentiable Reasoning to Self-supervised Embodied Active Learning. We are very glad to see you, Ruslan, and we are very glad that you accepted our invitation to participate in this conference. I would like to make a short introduction about you. Ruslan is a professor of computer science in the Department of Machine Learning at Carnegie Mellon University. He received his PhD in computer science from the University of Toronto, from this very famous now group of Geoffrey Hinton, for especially deep results in deep learning networks. And Ruslan also did obtained his master's degree. After spending two years postdoctoral years at Massachusetts Institute of Technology, he joined again the University of Toronto and later moved to Carnegie Mellon University. I would like to say that from 2016 to 2018, he was a director of artificial intelligence research at Apple. So I've checked your Scholar Google citations. They are enormous sightings, more than 127,000 of sightings. It's enormous for everybody working in doing research. So please take the floor, Ruslan. We are very glad to hear your lecture.
Thank you so much, and thank you very much for the invitation. You can hear me, right?
Right. We can see you.
That's okay.
Okay, let me share my screen, and I'll start.
Now we see this. Yes, that's okay.
Thank you very much again. Thank you very much for the invitation. So what I thought that I would do over the next 30 minutes is to talk about some of the research that's happening in my lab at Carnegie Mellon University. So many of you have seen the impact of deep learning in the space of speech recognition, vision, recommending engines, language understanding, even in places like drug discovery and medical image analysis. And ultimately, what we want to do is we want to build AI, we want to build artificial intelligence, we want to be able to build computer algorithms that can see and recognize objects around us, that can understand us, that can do some form of reasoning and understand natural language, that can move around autonomously, plan, explore, and in general display human-like intelligence. There are a lot of interesting research directions. So one of the big areas of research is natural language understanding and reasoning so that we can communicate with AI agents. Another area of research, big area of research, is what's called embodied AI. It has to do with reinforcement learning and control. Also, there's been a lot of work in incorporating domain knowledge into these complex systems, and I'm going to show you some examples, as well as dealing with models that can handle multimodal data, speech, video, audio, also semi-supervised and self-supervised learning. So let me first jump into natural language understanding and how do we incorporate prior structured knowledge. So when we think about deep learning, we typically think about inputs and outputs. Given an image, you're trying to predict what is it. Or given an English sentence, I want to translate it into French sentence. This is known as neural machine translation. But ultimately, if I ask you the question, which coronaviruses are known to infect people, there are multiple answers. How do we train systems to answer these complex questions? And this is where domain knowledge becomes important, maybe in the form of unstructured text or what kind of data you're feeding into your model. Knowledge bases, maybe tables. So how do we take this, a lot of data and put it into our models? And ultimately, we want to be able to do it in a fast way. The data is typically heterogeneous, meaning that it comes in the form of text, maybe it comes in the form of knowledge bases. And so how do we fuse that information together? How do we do reasoning so that we can look at information in different places? And also, how do we do it under weak supervision? So we don't have to specify exactly, how to answer specific questions. And I'm going to show you some examples of that. So one big area of research, again, and this is what's happening in IT companies, is building what's called knowledge bases. So for example, imagine that you look at Wikipedia articles or you look on the web and you find entities. You can think of them as some important concepts. So for example, if you're working in the medical domain, you might find these concepts or these entities to be important. And then you can also go and extract what's called relations about those entities. So for example, you can say diabetes is an instance of a disease, right? Or diabetes can be treated by a specific type of a drug. And a lot of research, again, focuses on how do we build these knowledge bases. Because if we can have these large-scale knowledge bases, then we can start answering questions. In fact, if you're using Siri or Google or even Yandex question answering type of a system, a lot of it is based on building these knowledge bases and mapping questions to specific entities and relations about this, and then you can answer questions. Now, when we think about doing some form of reasoning, we can think about the settings where, given the question, you might be able to retrieve, and let's say have a 50 million articles, Wikipedia articles, 50 million entities. What you can do is you can extract you can extract, let's say, 50 passages and 500 entities. So you can, based on the question, you can narrow down the search space. And then you can use what's called graph convolutional neural networks or deep learning type of approaches to answer the question. And this represents one of the forms of combining unstructured data, just data coming in the form of just unstructured language, for example, or like Wikipedia articles or news articles, with the knowledge base, something that you know about the world. And the question is, can you combine both of them to provide the answer? And there's a lot of work done in that space as well. And the way that it's working, let's say I ask you the question, who voiced Dog in a Family Guy? And that's Family Guy is a type of cartoon show. And you can basically say, well, given this question, maybe I can find a sentence that talks about, Family Guy includes a dog called Brian. And then you can find it in, your knowledge base, the concept Brian, and then you find the answer. Right? What's important about this particular structure is that you have the knowledge base, right? Manually constructed knowledge base, but you also have textual data. So you're fusing together knowledge base and text. And so the way that it's done is you can think of, given the question, you do some form of search. So here the question is being embedded in a form of, let's say, recurrent neural network or transformer architecture. And same thing happens with your knowledge base. Given the knowledge base and relationship between entities in your knowledge base and, let's say, sentences, you can use graph neural network to get the representation of each node. So effectively, you can think of each node as being enhanced by a corresponding sentence. And then you can apply what's called, again, graph convolutional neural network to do operations on the graph and get representation of the nodes. So this is just kind of a high-level idea of combining this notion of combining structured data, knowledge bases, with unstructured data such as text. And that's one way of combining what we call augmenting your models with domain knowledge, right? Because your knowledge graph is your domain knowledge. And in general, these types of systems, they work fairly well. So let's say if you have, if you're trying to answer questions, you can think of this as an accuracy, how well you're answering questions. If you're just using text only to answer the questions, you reach that performance. If you're using knowledge bases, you're reaching better performance. But then if you're sort of combining this knowledge graph with unstructured data, you can do much better. In particular, you can do much better in the places where you don't have your knowledge completeness is not high, right? So for example, here 30% basically means that you take your entire knowledge base and only retain 30% of it. Now, when we think again about these types of questions, we can also think about what's called multi-hop questions, which is another big area of research. So imagine I ask you the question like this. Which company, where is the company which manufactured voglibos headquartered? So voglibos is a specific type of a drug that treats diabetes. So to answer this question, you need to answer two questions. You need to answer the question of which company manufactures this specific drug. And depending on the answer, you have to find where it's headquartered, right? So for example, to answer the first question, you can maybe find from Wikipedia that it's a product of Takeda Pharmaceutical Company, Japan's largest pharmaceutical company. And then once you know the answer, you can find another piece of information that says this pharmaceutical company is located in Osaka, right? So the answer is going to be Osaka. Now, why this is difficult? This is difficult because these questions are unknown. Right? What that means is that you can think of them as latent variables or hidden variables that you need to extract. And that's why a lot of existing personal assistants like Google and Siri and Alexa, they can't handle these multi-hop questions because it's a fairly, a complex task. And humans are pretty good at being able to parse these questions and answer these questions. Right? And in that, again, to kind of find the answer to the question, you need to split the question into two sub-questions, find the answer to the first one, and given the answer from the first one, find the answer for the second. Right? So it's a fairly, these systems are, are quite fairly challenging to answer these questions, right? Because it requires some form of reasoning. Now, the way that, how can you do it, and can we do it efficiently? Can we do it in an end-to-end fashion so we can train the entire system? And can we do it compositionally? Right, so we can answer these questions. If it's what this is called two-hop question because you have to do two hops. There are three-hop questions and so forth. And here's a system that we built jointly with Google, with students at CMU. So here's the system just to show you. So let's say I ask you the question, which company founded by Steve Jobs was based in Redwood City, right? And this is what the system retrieves. The system retrieves that Jobs was the chairman of Apple and Jobs was a chairman of another company called Next. And then it retrieves the second passage that says that Next is another company that was based in Redwood City, right? So now the answer is Next. And just to show you, this is the system that's now analyzing 5 million Wikipedia articles, and it takes, I think, 1/10 of a second to find the answer, right? So these are the systems that operate in real time, really fast. They're analyzing 5 million Wikipedia articles, and they're doing a form of reasoning. And then what's highlighted in yellow is what the system believes is important information to answer the question, right? So the way that these systems work is you have what's called differentiable reasoning over the virtual knowledge base, but the idea is to use what's called follow relation. So given a set of entities, so given a set of, let's say, nouns, you follow relation to get to the answer, and then given this answer, you follow relation to get the second answer. So for example, to arrive to the answer. So for example, in our setting, X is the voglibos. That's the question that I'm asking about this particular entity. R1 is the manufacturer. So I'm going to construct the system that basically says, given X, follow relation R1 to find a set of answers. And given those set of answers, follow relation R2 to arrive to the final answer. And these systems, the way that they're built is given X, we do what's called soft entity linking to find a set of candidate choices. And then, you get the relation 1 using transformer architecture, get the relation 2 using a second transformer architecture. Now, the details, I don't have time to go into the details, but what's important to note here is the two things. One is that we have this compositional structure. So that's where domain knowledge comes in, right? It's not just a single deep learning architecture. Given the question, finds the answer. It contains sub-modules. Each sub-module answers a sub-question. And the second thing is the entire system is built in an end-to-end fashion, which basically means that given the answer, I can backpropagate the information through these subsystems back to the original question. So I can fine-tune the entire model in an end-to-end fashion. I don't have to build pieces separately, right? And again, this is end-to-end because we can backpropagate and update the model. And these models, they do, fairly well in terms of, especially if you do 2-hop and 3-hop questions. But what's important is that these systems are also operating in real time. So for example, they can answer 19 2-hop questions in just 1 second. And these models are running on a single GPU machine. So they don't require massive compute. Right? So they can, they work very fast. So now, and here's another question, if you ask the question, what is the shape of family viruses containing coronavirus? Then you sort of retrieving that, the coronaviruses belong to a specific type called coronavirare, and coronavirare is known to be spherical. And so again, you aggregating information across, you answering the first question, given the answer to the first question, you answer the second question, and then you provide the final answer. Right? And this brings us to kind of like this notion of how do we represent knowledge? Human knowledge is abstract. How can we build on these high-level concepts? We're building these systems where we have knowledge bases and we're having unstructured text, we're fusing it together, but how we go even beyond that, right? So that's a very big active area of research. Okay. Now, in the last 10 minutes, I also wanted to show you some examples of what's called embodied AI, reinforcement learning and control. So when we think about reinforcement learning, we typically think about learning behaviors. Given an input, you have an action, and your agent takes an action, or your robot takes an action. So when we think about physical intelligence, let's say you have an agent. The agent observes the environment, takes an action, and the agent needs to move around the world physically. You need to, whatever action you take will affect future observations, requires some form of spatial and semantic reasoning, right? And let's look at one specific example of what's called navigation. So given the observation, you pass it through the deep neural network, you have actions. Certain actions lead to good rewards, certain actions lead to negative rewards, and given that signal, you update your model. So this is known as an end-to-end learning. Now, when we think about goal-conditioned navigation, we can think about point goal. I give you coordinates and I tell my agent, go there. Or I give you an image and I tell you, my agent, find this image. Or maybe I give you an object goal, or maybe I give you language goals. For example, I give an instruction to my agent so that my agent can go and execute that particular instruction. And language is useful because it's convenient for humans. It has a notion of compositionality, right? So that ties together, question answering work with this idea of communicating with our agents, right? And one of the important things is the notion of exploration. How do we move around the environment and explore environment? Let me show you one example, a system that we built at CMU. Let me see if the video plays. This is an agent that moves around in the environment. These are virtual environments, but they're based on physical world. So you see this agent moves around, and this is the actual physical robot that moves around and does what's called object goal navigation. So here it's building the map. It's trying to understand what's around you, what's blocked, what's not blocked, where is the free space. And then it's essentially trying to figure out the semantics of the environment so that it can find or navigate to the correct location, right? And the entire system, the entire deep learning system is basically built on this little robot. And here's an example where I ask the robot to find potted plants. So it has to go and find the plant. As it moves around, it builds the map of the environment, and then it finds the plant. Right? Now, when we think about these agents, we think about how do we build systems that can understand the world. And a lot of work now is done from what's called static internet data, right? Somebody goes and labels examples for me, and I'm building my detection model, for example. But embodied data, the data that comes from the robot, is very different, right? It has a notion of, it has a notion of sequentially you're exploring the world, and the views are also quite different. So, for example, here's the system where if you're moving around, and you try to find a chair, this model says this is a chair, but obviously that's the wrong. Or here, you try to find a toilet and you're missing the toilet. The toilet is here, but you missed it. Because the training data is done on internet data, not on sort of these specific embodied environments. And again, when we think about this embodied data that our robots see, there is this notion of consistency through time, right? Objects just don't appear, disappear as you're moving around in the world. And now there's this notion in our research communities is notion of perception action loop. So the idea is that when you perceive the world, you can explore it and you can use it in a self-supervised way. So you don't require any supervision from humans. Right? You can go and you explore, and as you explore, you take actions. And then once you explore, you can do what's called visual learning. You can learn about this environment on your own. And the key concept here is called self-supervised, basically meaning that we don't need any additional labels. The idea is that you put the robot in your house, and the robot moves around, explores, and learns about the environment, right? So we've been building these what's called self-supervised embodied active learning systems, and it has two phases. The first phase is building a reinforcement learning agent that moves around and builds what's called 3D semantic map. So it's trying to understand the 3D world around you. And then the second phase, once you understand the 3D world, then we can use what's called temporal label propagation to actually figure out a better labeled examples for our system, right? So we can I'll show you examples where based on this 3D map, we can actually do what's called 3D label propagation and update our perception model. So notice that these two systems, it's more like you move around, you learn about the environment, and then you learn a better vision model. Then you have a better vision model, you learn more about the environment, you update your vision model, right? And everything is done in a self-supervised way, right? So here's an example. How do we build a 3D semantic map? So this is the 3D semantic map setting where the agent moves around in the world, and as it moves around, it builds this 3D map. And this is done using deep learning approaches. Right, and so here you can see that it's trying to figure out there's a couches here, there are tables here, there's a bed over here, right? So it builds the initial 3D semantic map of the world as it explores, right? Now, one of the things that the way that we're building this 3D semantic map is we're using reinforcement learning. And the way that we're using reinforcement learning is we say, well, look at this voxelized representation of the 3D map, sum across the length, across the height, across the breadth, and try to find a policy such that if you count the number of voxels with high confidence detections, that becomes your reward. So you're training a policy to say, find me as many confident objects in the environment as possible, right? And that now becomes your exploration policy. So the idea here is that don't just explore one object or don't move around places where you are uncertain about which objects you're seeing. Try to find as many objects as possible, and so that we are as confident as possible about what we found, right? Now, at the second stage, at the perception stage, what we can do is we can say, let's say we have this 3D semantic map, right? And let's say this is agent and this is what the agent is seeing. What we can do is we can actually use this instance label by doing 3D projection. So what we can do is we can say, well, this is the 3D map. This is what the agent observes. And using 3D projection, we can actually project the instance labels back in the pixel space, right? So for example, here you can note that the original model, the state-of-the-art object detection model, it actually fails to detect a chair here, right? But because we have a 3D map and we're seeing a chair here in our view, we can take this, project it here and say that's now a chair, right? And the reason why we can do it is because we're exploring, we're moving around this 3D world. And once we have the 3D world, we can actually project from different viewpoints back into the pixel space. And now essentially we're getting more labeled examples, right? This is another projection that where state-of-the-art object detection system didn't recognize this as a couch. But because in this view we have a couch, we can project it over here, right? And effectively what this gives us new labels, right? And these are false negatives. And again, these are the state-of-the-art system doesn't detect, but because we're building 3D semantic map by projection, we can actually get the labels, right? And this notion of consistency through time, because your 3D semantic map doesn't change, right? And so now, again, this is another false positive where the system says it's a chair, but there's no chair in our 3D semantic map, so we can say this is not chair. It's actually the table, right? And so now we can take these examples and basically retrain our perception model, create a better perception model, right? Because we have these false positives, false negatives. And again, one thing I want to emphasize is that the reason why we can recognize this as not a chair is because we moved around here and we've looked at this object from different viewpoints and we said, well, that's not a chair. Or we move around this particular couch, looked at it from different viewpoints and said, that's a couch, right? And that's where the 3D representation comes in, right? And this is just to show you that, on a specific data set, it's called habitat data set. It doesn't really matter. State-of-the-art object detection system gives you 34 accuracy in terms of this is average precision score at 50. But think of it as sort of, the notion of accuracy, how accurate you are. This is if you take the best state-of-the-art model. And now there's been a lot of work of trying to build systems that can improve on this number. And you can kind of like see very few of them improve. And if you use this self-supervised active exploration of the environment, you can actually improve the object detection by quite a bit. Right. And again, this is this notion that you learn about the environment as you're moving around the environment, right? You look at the chair and your state-of-the-art object detection system says, I don't know what this is. But if you move around this chair and you look at it from different viewpoints, then by using this 3D label propagation through time, you can actually, identify this as a chair and then retrain your model so that you look at it from different viewpoints and improve your detection system, right? So these are kind of examples, and it's kind of what we call generalization and specialization. Specialization is more of a setting where I put the agent in my house, I put the robot in my house, and my robot just explores it. And again, there's a big improvement in terms of in both detection and what's called instance level segmentation. And this doesn't require any additional label data, any additional supervision. So the agent just learns on its own. Right? And this kind of like comes to the notion of how do we build these systems when we train them in a simulation or something that looks like a simulation and bring them into the real world. And there's obviously, physical domain gap, visual domain gap. How do we take this into account? We've been sort of looking at the models that can bridge this gap because images can be different from the real world and the way that the robots move around can be different. And this is an example that you've seen at the very beginning where we take this little robot, we stick the model on top of it. And this is a simple Pi robot, which is Facebook's robot that they gave us as a gift to, be able to explore these environments. And I think that on that front, let me just mention that this sort of notion of building AI agents that can navigate autonomously, that can localize, plan, that can handle multimodal input like language and vision, that can move around. And so there's a lot of work again in the space of building intelligent agents that can build the semantic maps, understand the language, and how to combine everything together. And on that note, I'd like to thank you and thank all my students. And as a lot of this work is done by my students at CNU, and so thank you very much. Whoops. So, and I guess I wasn't sure. Yeah, I think that my time was up until 8 o'clock. Oh, sorry, up until I guess 3 o'clock. So I wanted to make sure that I finish on time.
Yeah, actually, you're right on time, but well, we still have 10 or 15 minutes so for questions, so just for talking. Thank you, Ruslan, for your talk. It was very straight and clean and exciting. So, Chairman.
Yeah, we would like people which are participating in the conference to ask questions. If there are any questions, okay, please. I would like to ask you, Ruslan, because you are working in a broad area, you told about also images, text, speech, and even you mentioned about something like drug discovery. It's completely different area of for people with a special expertise to work out. How you manage to work in this broad directions of application and maybe special data, because it was like in the previous that people working, for example, in images, they were completely different. That another community was working with signals and speech and chemoinformatics. You told about drug discovery is a completely far from this. How you manage to work in all these directions?
Yeah, it's a very good question. I think that you're right that, I think that a few years ago, we have language community and they working on language. We have vision community, they work on the vision. You have the entire conferences on drug discovery, medical image analysis, and they work in that space. I think what changed in the last few years is that you see more interaction between these communities because a lot of models, for example, this specific model that I've shown over here, these deep neural networks, the architecture is basically the same, and the modeling ideas and optimization, everything, for different types of inputs. So for example, a lot of us working on the vision, train the models, or you can actually make your input be, a language, and similar styles of models still work. Right? And so I think it brought multiple communities together because the underlying deep learning algorithms and optimization is the same, whether it's images or text or speech. Now, they become somewhat different and people do specialize, but there's also this big area of research, what's called multimodal learning, where you're combining representation from images, text, and speech. And I think a lot of us who work in the space of machine learning, we're somewhat, we use a lot of different data sets. So we work on images, we work on text, we work on speech, because to us, it's just a different type of an input. Right? Whereas before the deep learning was there, you had to process images in a very specific way. When I was a PhD student, for example, we were working on images and we were using something that's called GIST, which is kind of the representation you learn from images. And language community would be using something very different. And the two wouldn't be transferable. You couldn't take, the feature extracted that you're using in images and apply to speech, for example, or language. And so I think it's the deep learning models that started uniting a lot of these different communities. And so because the same technique exact same technique can be applied on language or on speech or on vision. So that's the reason why there is a lot of kind of, connections. And ultimately, when we're building these agents, I think the goal in my lab and most of my students, we're interested in, the setting of where the agent actually receives multimodal inputs. For example, one of the work that I haven't shown you here is we're working on instruction following. So the agent not only needs to explore and build this environment, but it also needs to understand instructions, where a human says something in natural language, like go to this room, pick up the cup, take the cup, move it to the kitchen, for example, right? And so this is sort of this is the next level of combining language, vision, and this 3D understanding and reinforcement learning.
Okay, thank you very much. And how do you think now students at the university, especially I mean students working in or studying computer science, maybe mathematics, informatics, they are they're interested very much in this machine learning, and especially in deep learning approaches. They are trying to apply these models for solving various problems using their course or diploma papers, but they do not know, in fact, the basic algorithms which were developed during many years, for example, in image processing. They do not know how to process images, how to extract features, and is it important to know, or it just now something which is not very important, all this stuff which was developed earlier, and just take this new technology and you can solve every problem?
That's a very good question. I think that it's very important to know about all the previous and as well as all the different algorithms that people used, because sometimes what's happening is it's the combination of both that gives the best performance, or sometimes you can look at the insights of how images. So for example, I can give you one example in speech. In speech, there is a lot of work done on applying these deep learning models on a raw speech signal, and as well as applying these deep learning models on transform features like MFCC, for example, which is a specific technique for pre-processing audio, and then using deep learning on top of it. So I think it's important to know all of these different algorithms, because ultimately you can think of deep learning models. The key idea of these deep learning models is that you can update the parameters. So you can fine tune them to a specific type of data that you're working with. But I think it is important to know about all the approaches, all the previous approaches people were doing, because sometimes these approaches give inspiration for the types of architectures or for the types of models that we're using. So for example, in the vision domain, 20 years ago, 30 years ago, people discovered that the first level of representation learned something was called Gabor filters. These are oriented edges. And deep learning models learn these things, but a lot of, initial kind of, optimization techniques and everything were inspired by looking at what these previous approaches were doing. Right. So I think it is important to know, what techniques were used before, because in many cases, especially if you start working with a new data set, like with medical images, for example, they have very different statistics, very different structure. And so you need to understand how people processing the data, what techniques are used, so that you can design a better, let's say, deep learning model. Right.
Okay. Thank you. Maybe somebody else would like to ask questions. We have still 5 minutes.
Yes.
Yeah, I got some.
Yeah, please.
Okay. By the way, that previous discussion very closely related to discussion how we study cognitive abilities of the brain. Some people believe that we should go to cellular level and we understand how signal penetrate, etc., etc. Some others says, "Oh, that's stupid idea. We should to understand how it works on macro level, on the high level. Otherwise, we just losing the point." Anyway, that was not my question. Actually, just comment. So my understanding is that you make some kind of emphasis to graph networks. So that's the reasonably complicated things. I only got one student who did it, but I'm working in medical imaging domain, so graphs is, in my understanding, this approach, graphs are used because it's like old school approaches and that generation of artificial intelligence where they put the knowledge, represent the knowledge in graph form. So, okay, that's my understanding. Maybe I'm wrong. So, but this is not the question. The question is, I can imagine easily that diagnosis in medical domain is represented by graph. Because it's combined different sort of data, that's very natural to do, to deal with, like blood pressure, number of percentage of leukocyte in the blood, and some medical images altogether. But do you think it is possible actually to use these graph networks to efficiently analyze medical images? Just one single sort of data, just images. And so, if so, then it's how it can be done.
So it's hard to. So the way that I think about, there are graph-based applications on analyzing images, but when I think about graphs, I typically think, at least in my research, I typically think about, let's say you have an image, you extract some features, and then you can potentially build some kind of graph on top of those features. Right? That's one way of doing it. But when I think about graphs, typically I think about, in a language, I guess it's very commonly used because you can build these knowledge bases. I think in the medical image kind of like analysis, you can do something similar. If you find this type of feature and you find this other type of feature, then you can combine, an explicit graph by humans that basically says that, if you have certain types of representations you found, then that means something else. Maybe let me show you one example.
Yes.
So, there was one example of people trying to, for example, this is done in the setting of images, but let's say you're detecting in this image a big tail, you're detecting a big nose, and you're detecting this animal. And then you have something that's called a graph that basically says, well, you're detecting tail, trunk, and mouse. Right? So you think it's a mouse, but it has a big trunk and a big tail. And then you have a knowledge graph that says, well, if a mouse has a big trunk, so like a big nose, then that basically is what's called elephant shrew. It's a type of an animal. Right? And you can detect this, or you can learn this without having a lot of labeled examples. Right. So it's more in the setting, I think, where you can potentially do well is in the setting where you find these pieces, different features. And if you find these different features and you have a graph that tells you if these features exist, then that means it's this type of an animal, or it means that it's this type of diagnosis. If these other types of features you discover, it means that maybe it's this other type of diagnosis. So this is where the human knowledge comes in, right, or some form of right, because then it's hard for deep learning systems to learn it on its own, unless you have lots and lots of examples, unless you have a lot of medical images for that specific diagnosis, right? So if you have thousands of examples of elephant shrew, you probably don't need the graph because you can just map it to what the correct answer is. But if you have a complicated data set, complicated images with millions of different features, and you don't observe most of them, then this graph type of representation can potentially help you.
Okay, thank you very much. I still have one more. Is it possible to ask? It's not medical anymore.
No, Vasily, we already
okay.
already out of schedule.
We have one
So-
question from the chat, actually, so I propose to our speaker, because it's in the Zoom, to ask
there is
it
a
orally.
thing in the chat. Yeah. What do you think about multi-agent strategy? Yeah, I think that just very quickly, multi-agents is another area of research. And I think that there is some work. We haven't done a lot of work, but yes, you can have 2 agents or 3 agents exploring the environment and finding kind of, jointly in collaborative ways, sort of, let's say, explore the environment. So there's some work done in that space. You can put 2 agents. You just have to design what's called communication protocol between multiple agents, so that they explore different parts of the environment, or in a collaborative way.
Unusual, but it was exactly my question about swarm vision, about this, whether you need to build up model or not. Geometrical. Okay, thank you very much.
Of course.
Okay,
Yeah.
okay. Thank you very much. Ruslan, I would like to thank you a lot for your very early. It's very early now in the United States. Your presentation, but it was very interesting for us to know about the research you are doing now, and you are interested. You are very active. I've seen at your website that you publish a lot of various your results obtained. So thank you very much once more for your participation and your agreement. Goodbye.
Thank you, Ruslan, from myself. So because of this time lag, so despite of this, you're still with us, and I'm very happy to chat with you before the conference, and hope to communicate further. Thank you again.
Absolutely.
Yeah.
Thank you.
Thank you so much.
Goodbye.
Bye.